Finish out the course here talking about parametric equations. You can think of parametric equations as generalizing the concept of function. So up till now, when we've been thinking about a function, we get a real number, input, say t. We have some process f we associate with that real number t to get a real number output, f of t. And to be a function, each input is going to give only one output. So with parametric equations, what we do is we associate a real number t with two functions. So an f and a g, each on their own functions, and then we pair them together to create a point in the plane, f of t, g of t. So the long and short of it is I'm taking a real number and I'm associating with a point in the plane. So for example, let's say you're sitting on your table outside enjoying a picnic or something, and you happen to see an ant or some other bug on the table, and it starts crawling from a point O, and it crawls around on the picnic table. Then for every time t, the ant is only occupying one location. And so we can think of t, the time, being associated with whatever point p of xy it's at that one given time. So not only does that give a curve as the ant walks around, it also gives an orientation. It gives a direction that the ant is traveling. And so I like to think of parametric equations as being used to describe trajectories. Okay? So let's do an example. I finish out the course here talking about parametric equations. You can think of parametric equations as generalizing the concept of function. So up till now, when we've been thinking about a function, we get a real number, input, say t. We have some process f we associate with that real number t to get a real number output, f of t. And to be a function, each input is going to give only one output. So with parametric equations, what we do is we associate a real number t with two functions. So an f and a g, each on their own functions, and then we pair them together to create a point in the plane, f of t, g of t. So the long and short of it is I'm taking a real number and I'm associating with a point in the plane. So for example, let's say you're sitting on your table outside enjoying a picnic or something, and you happen to see an ant or some other bug on the table, and it starts crawling from a point O, and it crawls around on the picnic table. Then for every time t, the ant is only occupying one location. And so we can think of t, the time, being associated with whatever point p of xy it's at that one given time. So not only does that give a curve as the ant walks around, it also gives an orientation. It gives a direction that the ant is traveling. And so I like to think of parametric equations as being used to describe trajectories. Okay? So let's do an example. Example 1, sketch the curve described by, and this is how you're typically going to be presented with parametric equations. It's a system of equations. They're coupled together. X is given by some function of t. Y is given by a potentially different function of t. What I'm thinking of t as being time is more formally called a parameter. So if we wanted to start sketching this graph, we can go back to how we sketch graph of functions back in college algebra by plotting points. So we can make a little table of values here. We'd have the t values, the x values, the y values, and then the point on the curve x comma y. So they say to start t, t is greater than or equal to -2. So we could start at -2 and then plug in some friendly values for t. So -2 to 2, say. To figure out the x coordinate that's going to go with these times, we just plug t in and simplify. So negative 2 squared minus 3. 4 minus 3 is 1. Negative 1 squared minus 3, negative 2. Negative 3. Negative 2. And then back to 1. So those are the x values. To get the y values, I'm going to plug these values into the equation for y. So negative 5, negative 3, negative 1, 1, 3. And then I'm going to look at the pairs x comma y. So the point on the plane is the x comma y. So 1, negative 5, negative 2, negative 3, negative 3, negative 1, negative 2, 1, 1, 3. All right, so go ahead and graph this here in the xy plane. So 1, negative 5, negative 2, negative 3, negative 3, negative 1, negative 2, positive 1, 1, 3. And now I connect the dots in a pleasing pattern. So it looks kind of parabolic. We'll talk about that more in a minute. But if I look at how I connected the dots, I connected the dots as t increased. So this was the point corresponding to t equal negative 2, t equal negative 1, etc. This endows the curve with what we call an orientation. So once again, orientation is the way that the curve is traced out for increasing values of t. Now, this certainly looks like part of a parabola, and you can kind of see that happening here. So once again, the parametric equations, it's a system of equations. The t connects the x and the y because it's the same t in both. So what we can do, treating this as a system of equations, we can go back and learn what we did and do what we did in algebra with substitution and elimination, and we can eliminate the parameter. In other words, we can attempt to get, this isn't always the case we can do this, but we can attempt to just get a relationship between x and y, right? So what we can do is, algebraically, one technique is to pick one of these equations and solve one of them for t in terms of x or y, whichever is easier. So I'm going to select the second equation here. So I'm going to look at 2t minus 1 is y, and I'm going to solve this equation for t. So I'll add 1 to both sides. So 2t is y plus 1, then divide by 2, y plus 1 over 2. And this is my value for t, which I'll substitute back in for x. So x is equal to the quantity y plus 1 over 2 squared minus 3, which I can simplify a little bit. This would be y plus 1 quantity squared times a quarter minus 3. And you might think back to the conic sections. If we solve this for y plus 1 squared, that's going to be 4 times x plus 3. By golly, this in fact is a parabola, with the vertex at negative 3, negative 1, that's opening to the right. And so if I look at my graph here, sure enough, this does look like a parabola. That does look like the vertex. Now, if you were to graph this back in college algebra, if you go to graph it back there, you've got the vertex negative 3, negative 1, and then you could figure out where the focus and other points are. Okay, so but you would get the entire parabola. So when you eliminate the parameter, you're going to eliminate any restrictions on the curve given by the parabola, or given by the parameter, but also you're going to lose the orientation of the curve. But it will tell you what the trajectory is. So in other words, we could say that this trajectory is lying on the parabola, y plus 1 squared equals 4x plus 3. So let's see. Look how Desmos. Let's check out Desmos here. See how we can do some of these things on Desmos. We can make the table on Desmos. So if we hit the add item and go down to table, we're going to call our inputs t's. So we'll call that a t1, and then we're going to have f of t1, and then g of t1, and we're going to take. We don't want the individual points for that. And then I would define my f of t. So what's my f of t? T squared minus 3. G of t is 2t minus 1. And once again, we're not concerned with the graphs of f and g individually. We want to pair them up. So then I can just type in the values here, -2, -1, 0, 1, 2. All right. So this can help us reproduce the graph. If we wanted to graph the system of parametric equations itself, we can tell Desmos to graph f of t comma g of t, just like that, and we can arrange the parameters. So -2 to, well, on to infinity. So -2 to, say, I don't know, 10 or something. And so we can see that there. And then we can check that that really does live on that parabola. What was the parabola again? Y plus 1 squared equals 4 times x plus 3. And you can see there's our trajectory, and there's that parabola. So that does check that it lives on that curve. Okay, so this is how Desmos can be used to help us with these things. So let's look at a couple more of these curves. So we can plot some points. We can try to see what curve it lives on. Let's take a look at number 1 here. X is e to the minus t, y is e to the minus 2t, and this is for t bigger than or equal to 0. Now we know with great exception that outputs from exponential functions are going to be some zany decimals. So let's take a look here. Let's just adjust these things. The cat's very excited about this, as you can tell. E to the minus t, e to the minus 2t. And let's hold off on the graph for now. And we would just plug in numbers bigger than or equal to 0. So like 0, 1, 2, 3, 4, 5, etc. And here come the decimals, right? So we got the decimals here. 1, 0.36, 0.13, 0.09. So these are, we're starting here at the 0.11. So I guess I can do that. So if I look here, we've got the plane here. So I'm just gonna so when t is 0, we're at the 0.11. And then 0.36 comma 0.13. So at 0.36, so like around a third, we're at 0.13. And then at 0.1, we're at 0.01. So we can see what's happening is that we're heading down this way. Okay, we're heading down this way. And as t gets bigger and bigger and bigger, these numbers get really smaller and smaller and smaller. Once again, this is scientific notation. So this means we're basically taking this decimal and dividing it by 10 to the 5th power. So we're putting 4 decimal places in front of this 4. Right? So as t goes off to infinity, right, the point xy is heading into 0, 0. Right? So it's getting smaller and smaller. It never actually gets there, though. All right? So that would be one of those, there'd be a hole in the graph there. But we could try to analyze what curve that is. Right? So we can try to eliminate the parameter here. X is e to the minus t. Y is e to the minus 2t. We can try to eliminate the parameter here. Now we could actually solve for t by taking logs and stuff, or we could recognize that, you know what, I've got the same base, and the exponents, this exponent is just double that exponent. So I could rewrite y as e to the minus t squared. And so I can see right away that even though this looks very complicated, this parametric curve is actually just sitting along part of the parabola y equals x squared. And so we can once again check that out. So we could have Desmos actually graph force. We're starting at 0 here, so there it is. And then we'll graph y equals x squared. And sure enough, we can see that the graph of the parametric equation does lie along that parabola. Okay, let's get some trigonometry involved here. So we've got a couple circular functions, sine of t and cosecant of t. And this is strictly for t between 0 and pi. You can see why it's got to be strictly between 0 and pi, because cosecant's going to have issues at 0 and pi. So let's go ahead and fire up Desmos here. F of t is sine of t. G of t is cosecant of t. We're looking strictly between 0 and pi. So as I mentioned here, it's going to be undefined at 0. So let's plug in some friendly trig numbers, like, I don't know, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi's over 3, 3 pi's over 4, 5 pi's over 6, right? And once again, we know what these numbers are, right? I mean, these are decimal approximations, but for example, we know that that's square root 2 over 2, and that's square root 2. All right, we know that's square root 3 over 2, and this would be 2 square root 3 over 3. All right, thus, you know, and so on down the line here. Okay, so if we look at what's happening here, once again, we can't get to pi, we can't get to 0. But if I look at applying these points, a half comma 2. Oh, let me there we go. So that would be 1. So a half comma 2, and then 0.7-ish, 1.5-ish. So 0.7-ish, 1.5-ish. 1, 1. Wait, hold on, I messed that up. So that's a half 2, 0.7, 1.5, 1, 1. Point roughly. Well, now we're back to this point. So yeah, so and this is something that interesting happens. So then I'd be like, so now you see I'm retracing these points. So I come down here. So I'm coming down this path, and then once I get to 1, I actually reverse direction and go right back up. You see I'm retracing the same points. Okay. All right, so it kind of comes down and then goes back up. All right. Now once again, if we wanted to try to see what curve we're tracing out there, and well, I guess more importantly, what's going on at the 0 and the pi, right? So as we get closer to 0, we can plug in some numbers that are really close to 0 here. Actually, we'll just graph this. Boom. Whoops. We'll graph this. We'll go 0 to pi. And so we can see what happens is we actually get a vertical asymptote here. So let's see if we can explain that by eliminating the parameter and looking at what's going on here. So x is sine of t, y is cosecant of t. which is 1 over the sine of t. So just like in the previous example, I don't really need to solve for the parameter t itself. I can see the relationship y equals 1 over x. All right? And I know that as t goes to 0 from the right, what's going to happen? X is going to go to 0 from the right. X will become a small positive number, which means that the y is going to go off to infinity. And the same will happen as t comes into pi from the left. As I plug in numbers that are angles that are closer and closer to pi but less than pi, the signs get closer and closer to 0 but are positive, and so the y, which is the reciprocal, is going to blow up to infinity as well. So this curve that's happening here on Desmos, this is the curve y equals 1 over x. So we can see that. And what's happening is that with the parameterization, we're heading down the curve until t equals 1, and then we're turning around and heading back up the curve. So as t goes to 0 from the right, we're going to that vertical asymptote, and the same as t going to pi from the left, we're having that vertical asymptote. So we're coming down the curve, turning around, and heading back up. So you can think of this is the graphical depiction, really, of the reciprocal identity. Is really what that is for cosecant. All right, last example here. We're looking at x equals 1 plus 3 cosine, y equals 2 sine. So we got some friendly trig functions here. So 1 plus 3 cosine t, and then 2 sine t. And we're running angles from 0 to 3 pi over 2. So we got some friendly angles here. 0 to 3 pi over 2, so we can do 0, pi over 4, pi over 2, pi, 3 pi over, let's see, pi over 2, oh, let's do the 3 pi over 4, pi, 5 pi over 4, and then 3 pi over 2. So those are some friendly numbers between there. If we need more, we'll put in more. And once again, we know what these exact values are, but these decimals help us graph it. So we start off here at 4, 0, and then we're at 3 point something, comma, roughly 1.5. So there. Then we're at 1, comma, 2. Yeah, 1, comma, 2. And then we're at roughly negative 1, comma, 1.5. So negative 1 there. Negative 2, 0. And then negative 1, comma, negative 1.5. And then 1, negative 2. Okay. So if I connect the dots in a pleasing pattern, it looks like I'm tracing out part of an ellipse or a circle. Let's put the orientation on there. So we're traversing things counterclockwise. So let's see if we can figure out what curve I'm traversing here. So we take a look. Once again, we want to eliminate the parameter. We don't need to solve for t necessarily. But for example, in the first equation, I can solve for cosine. So I can take x and subtract 1 and divide by 3. And the second equation, I can solve for sine by just dividing both sides by 2. And I can eliminate the parameter using our favorite identity, cosine squared of t plus sine squared of t equals 1. You may not have thought about this identity this way, but on the left-hand side, I've got two functions of t, and on the right-hand side, the t is gone. So I've eliminated the parameter there. So I'll plug this in. X minus 1 over 3 squared plus y over 2 squared equals 1. And that's going to get me x minus 1 squared over 9 plus y squared over 4 equals 1. And once again, you may recall this is an ellipse. The center of the ellipse is at 1, 0. I go 3 units left and right from the center and 2 units up and down from the center. And so if I go back to my graph here, right, the center was 1, 0. So this would be the center of the ellipse. I would go 3 units to the right and 3 units to the left. So that would, see, that's 1, 0. I would get to, there's the 4, 0, there's the negative 2, 0, and then 2 units up and down. That would get me up here to 2 and minus 2. And I can double check this. So I can graph that. I want here the t to go from 0 to 3 pi's over 2. And I can double check. X minus 1 squared over 9. Whoops. Plus y squared over 4 equals 1. And then you can see there, once again, we lose things. Like, for example, for this ellipse, we only want 3/4 of the ellipse. We also have that counterclockwise orientation. We lose both of those things when we eliminate the parameter. But when we do eliminate the parameter, that confirms that we are traveling along an ellipse. Okay, so there's a few examples of parametric equations. Here's the equation, graph it. You've got some technology you can use to help you generate those points, and you've got some algebra to use to confirm your suspicions. Some examples of, given the parametric equation, sketch the graph, describe the graph. We can go backwards and come up with parameterizations for common curves. And once again, the advantage to this is that for curves that are ellipses, we can use, for example, number 3 here, these functions trace out an ellipse. We can use what we know about functions to analyze these curves now, and then of course moving into calculus, that we couldn't normally do, because the ellipse itself is neither a function of, y is neither a function of x nor x a function of y. So sometimes we want to come up with parameterizations to take advantage of some things. And so this is a recipe list, and we'll just sort of go through an example of each to show you, give you an idea of why these are what they are. For example, I want to parameterize y equals x squared from x equals negative 3 to x equals 2. We can do a very cheap parameterization for this. You know, sort of the low end here. We can just let x be t, and then we'll let y be t squared, as x, aka t, runs between negative 3 and 2. This is a parameterization. You can see instantly that y equals x squared, because I'm just letting x be the parameter. Okay, but this will be a handy way to parameterize this line segment, or this part of the parabola. And once again, you can check this on Desmos to see that it's doing the job. So we can just do f of t is t, g of t is t squared, and we're just going to go from negative 3 to 2, and then we can put y equals x squared up there. So if we look at this, whoops, there it is, there we go. Okay. Number 2, y equals f inverse of x, where f of x equals this. So you may remember inverses. To get the equation for the inverse, you would start off with saying y equals f of x. So y is x to the 5th plus 2x plus 1. But then to get the graph of the inverse, this would be the graph of the function. To get the graph of the inverse, we interchange the x and y. The inputs and outputs switch. So this would be x equals y to the 5th plus 2y plus 1. All right. Now this would be something that Desmos could graph no problem, but like back with the graphing calculators and the more archaic technology, this might be a challenge, but not with parametrics. Because now we can just do a cheap parameterization here. I can let y be the parameter t, and then x would be t to the 5th plus 2t plus 1. All right. So let's see. Let's check on Desmos here. So my x is t to the 5th plus 2t plus 1. And then my g of t is t. And, you know, they don't give us any restriction, but looks like it kind of levels off there. And let's just graph x equals y to the 5th plus 2y plus 1. So we could graph that. Or we could actually graph the original function like that. And then we could graph the line y equals x. Because remember this, if we reflect the graph of the original function across the line y equals x, we should get the inverse. Okay. There's a little college algebra review for you there, here at the end. Okay. Number 3, the line segment which starts at 2, -3 and ends at 1, 5. So starts at 2, -3 and ends at 1, 5. Of course, it had to be 1, 5 way up there. All right. So we're trying to parameterize this line segment. Like that. Okay. Okay, so here's how we're going to do this. We want to think sort of back to vectors with initial point and terminal point. Here's the basic recipe for line segments. X is going to be your initial x value, where you start, plus your change in x times t. Y is going to be your initial y value, where you start, plus delta y times t for t between 0 and 1. All right, so it's kind of like we're starting at the point x naught, y naught, and then after 1 unit of time, we want to be at the other point. All right, so what's this look like here? In this scenario, what would it be? X would be, I'm starting at the x value 2, and what's my delta x? My delta x is 1 minus 2 t. The y value starts at -3. What's the delta y? We end at 5 and start at -3. So if I clean this up, this is 2 minus t, and this would be -3 plus 8t. So basically what we're saying is I'm going to start at x equals 2, and I'm going to move -1 unit in the x direction. That would take me to 1. I'm going to start at -3. I'm going to move +8 units in the y direction to get me to 5. And this will happen over the span from t equals 0 to 1. Right? So when t equals 0, these cancel out. I should be at my initial point. So when t equals 0, I'm at the point 2, -3. And then after 1 unit of time, I've added the delta x and the delta y to each of the x and the y. So after 1 unit of time, I'm adding the -1. So 2 minus 1 gets me to 1. And then I'm adding the 8. -3 plus 8 gives me 5. All right? So it's where you start plus the change times t. Where you start plus the change times t. T runs from 0 to 1. All right? So that's how you can parameterize line segments. Once again, we can look at this on Desmos. So 2 minus t, -3 plus 8t, and t is going from 0 to 1. And we can check here 2, negative 3, and 1, 5. And there it is. Okay. All right. Okay. The circle x squared plus y squared minus 4y equals 4. All right. So when we saw the ellipse in the previous example, so thinking back to college algebra, we can put the circle into standard form by completing squares. So the first step here is to put this into standard form by completing the square. So we've got 1x squared plus 2x. So I'm going to cut that coefficient of x in half. That'd be x plus 1 quantity squared. Cut the coefficient of y in half, y minus 2 quantity squared, and that equals 4. Now when I square this out, I'd get my x squared plus 2x plus 1. When I would square this out, I'd get y squared minus 4y plus 4. So I would get x plus 1 squared plus y minus 2 squared equals 9. And I can then divide the 9 through x plus 1 squared over 9 plus y minus 2 squared over 9 equals 1. All right. So the goal here is we've got a sum of squares equaling 1. And that should remind us of the identity cosine squared t plus sine squared t equals 1. All right? So that's kind of where this comes from. So once again, doing a little bit of work and putting things in standard form. We got a sum of squares equaling 1. So I'm going to think of this as cosine squared t plus sine squared t. And all I'm going to do is just look at what's being squared here in the x. The first term, what's being squared, is x plus 1 over 3. So basically take the square root of that, if you will. And I'll set that equal to cosine. Look at what's being squared here, y minus 2 over 3, and set that equal to sine. And then I'll just solve for x and y. So I'd be multiplying by 3, and then subtracting 1, multiplying by 3, and then adding 2. And if we want to go once all the way around the circle counterclockwise, right, I'd let t run from 0 to 2 pi. So when you have circles and ellipses, you want to go in and put things in standard form so that you get a sum of squares equaling 1. Right? You got something squared plus something else squared equal 1. Think of this identity. So let's go ahead and check this for you. Let's see. 3 cosine t minus 1, 3 sine t plus 2. We're going from 0 to 2 pi. Boom. And now let's look at x squared plus 2x plus y squared minus 4y equals 4. And you can see there the graphs are indistinguishable. Okay. Now, this actually goes back. So you know, we've come full circle, pun intended, because if you think about it, when we define the sine and cosine of real numbers on the unit circle, how did we do it? We defined x as cosine of t and y equals sine of t. So the very definition of sine and cosine on the unit circle from the unit circle is a parameterization of the unit circle. All right, so there we are. Okay. The left hand of the ellipse. So the left half, rather, of the ellipse. All right. Once again, I've got x squared plus y squared, or the sum of two squares equaling 1. what's being squared here? So I want to think cosine squared t plus sine squared t is 1. What's being squared here in the first term is x over 2. So x over 2 would be cosine of t. So x would be 2 cosine of t. What's being squared here? Y over 3. So that would be sine of t. So y would be 3 sine of t. All right. Now if I want to do the left half of the ellipse, I think about going around the circle. The left half would start at pi over 2 and then go to 3 pi's over 2. So that should work here. Pi over 2 to 3 pi's over 2 should just get me the left half of that ellipse. All right. So let's check it out. Let's see if that works. So 2 cosine t, 3 sine t. And I just want to go from pi over 2 to 3 pi over 2. There we go. And then we can check x squared over 4 plus y squared over 9 equal 1. And so there we got the left side of that ellipse. And once again, the orientation here is we're going counterclockwise. Okay, so that'd be a counterclockwise orientation. Okay, so once again, you can think of this is a recipe list. All right, this is a recipe list. At that last curve again. So once again, this is a counterclockwise parameterization starting with t equals pi over 2. Well, what if you didn't want it counterclockwise? What if your trajectory you wanted to model was clockwise? Well, we'd have to reverse the orientation. So how do we do that? All right, well, we're going to start with the parameterization we have, 2 cosine t, and y is 3 sine t for t between pi over 2 and 3 pi's over 2. And if I want to reverse the orientation, I'm just going to basically run time backwards. So I'm going to replace t with the opposite of t. So I'd have x being 2 cosine of the opposite of t. Y is 2 sine of the opposite of t. Pi over 2 goes, minus t runs between minus pi over 2 and 3 pi over 2. And then I can simplify. The even property of cosine, I just keep writing that. I keep writing that down. Even property of cosine. Cosine will absorb the negative, so x would be 2 cosine t. And the odd property of sine means y would be negative 3 sine of t. And to solve this inequality, I would divide through or multiply through by negative 1. That's going to reverse the inequalities. All right. So this would be good then for negative 3 pi over 2 less than or equal to t less than or equal to negative pi over 2. This would give us the same curve, just the orientation is reversed. All right. And you could check that. You could plug in the negative 3 pi over 2. Cosine of negative 3 pi over 2 would be the same as the cosine of 3 pi over 2, which is 0. The sine of negative 3 pi over 2, the negative will come out. So we get 3 times the sine of 3 pi over 2, which would be negative 3. So that tells us that we would be starting down here. And then we would be working our way up to when t is negative pi over 2. Once again, the cosine of negative pi over 2 would be 0. The sine of negative pi over 2 would be negative 1 times negative 3 would get us back up to here. Whoops. Okay. All right. Well, what if you wanted to do a time delay then? Like, because, you know, let's say, well, all right, I've got it going the right orientation, but now I want it to start at t equals 0. So how can we adjust that? Whoops. So basically, this thing is already over. It's already over before t equals 0 even starts. Okay, so what if I want to delay this thing by 3 pi over 2 units? So I want to do a time delay of 3 pi over 2. So what I would do is I would replace t with t minus 3 pi over 2. All right, so this is introducing a time delay. So I would do 2 cosine t minus 3 pi over 2, negative 3 sine t minus 3 pi over 2, where it's t minus 3 pi over 2 runs between negative 3 pi over 2 and negative pi over 2. And now we would simplify these. So once again, we can use identities here. If I look at the sum and difference formula for cosine, we would get cosine of t times the cosine of 3 pi over 2, which is 0, plus the sine of t times the sine of 3 pi over 2, which would be negative 1. So this would end up being negative 2 sine of t. Using the difference formula for sine, we would get sine of t cosine of 3 pi over 2, which once again is 0, minus cosine of t times the sine of t, or sine of 3 pi over 2. So the sine of 3 pi over 2 would be negative 1, times the minus, which would be a plus 1, times the minus 3. So this would be a minus 3 sine, minus 3 cosine t. And then if I add 3 pi over 2 through this, adding 3 pi over 2 here gets me to start at 0. Adding 3 pi over 2 here gets me to pi. And so let's check that this actually works. So minus 2 sine minus 3 cosine. So minus 2 sine of t minus 3 cosine of t. We want to go from 0 to pi now. Boom, there's the left-hand side. And we can check the orientation here just by looking at these points, right? So we start 0, 3. So we start here, and then we're at negative 1.5, negative 2-ish, and then negative 2, 0, and then negative 1.5, 2-ish, and then 0, 3. So by golly, that does work. So now we've got a clockwise representation of this that starts down here at t equals 0, ends up here at t equals pi. Okay. Close out the section, the chapter, and the course looking at a very interesting curve called the cycloid. Now, the cycloid has some very interesting properties, interesting history associated with it. Be a great project. Here's what the cycloid is. We're going to start with a circle of radius r, and we're going to roll it along a horizontal path at a constant velocity v. So if I start here, we're going to imagine looking at the point at the bottom of the circle, and as the circle rolls down to the right, we're going to be tracking the point on the circle as it rolls around. Now there's two components of this motion here. We've got the rotation on the circle, and then we've got the horizontal translation occurred by it rolling down this path. So we're going to look at each piece. We'll start with the rotation piece, and then we'll add in the horizontal piece. So let's just look at the rotation here. So we're on a circle of radius r. So if we just look at this, x squared plus y squared is r squared. We can divide through by the r squared, and we get our sums of squares again. So we can think, okay, they're using theta here for the parameter. So cosine squared theta plus sine squared theta is 1. We can think about that identity. And that's going to lead us to our parameterization. X over r would be cosine of theta. Y over r would be sine of theta. So x is r cosine theta, y is r sine theta. And if I do the usual, theta runs between 0 and 2 pi, this is going to give me a counterclockwise orientation starting at the point r comma 0. What I need is I need a clockwise rotation starting at the point 0, negative r. So I'm going to have to adjust my parameters like I did in the last example. So first off, let's get the orientation correct. So we need to reverse the orientation. So I'm going to replace theta with the opposite of theta. So x is going to be r cosine minus theta. Y is going to be r sine minus theta, where minus theta runs from 0 to 2 pi. And we can simplify that using the even and odd identities. So x would be r cosine theta, y would be minus r sine theta, and negative 2 pi would be less than or equal to theta, less than or equal to 0. All right. So now we've got the right orientation, but I'm starting at negative 2 pi and going to 0. So at negative 2 pi, I'm starting here, and then when I get to, for example, negative pi over 2, or excuse me, negative 3 pi over 2, so if I plug in the negative 3 pi over 2, I'd be down here. Okay, so I'm starting at this point and moving counterclockwise. All right, so I want to start at this point. So I want to start at the negative 3 pi over 2, in other words, to start at the bottom, and then to go once around, I would just be adding 2 pi to that. So remember, any 2 pi length of interval is going to sweep out one trip around the circle. I want to start her at the bottom point, so I want to start at negative 3 pi over 2. And then if I go, I'd have to go all the way back around to positive pi over 2 to get back to the bottom. All right. Okay. Now this is perfectly fine. So I'll just write it again here. So this does the job, right? This has a clockwise rotation starting at the bottom here, but we might want to shift things so things start at 0. So this is where we can introduce that time delay that we did in the last example. We need to delay things by 3 pi over 2. So let's go ahead and shift theta to theta minus 3 pi over 2, both here and down there. So my bounds on the theta, when I add the 3 pi over 2 across, are now going to be back to 0 to 2 pi, all right, which is comforting, or at least starting at 0. And then I can apply those sum and difference formulas we did earlier to convert the x and the y. So for x, we're going to have r times cosine of theta, cosine of 3 pi over 2. Well, the cosine of 3 pi over 2 would drop out, that's 0, plus sine of theta, sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. So like before, we're going to get a minus r sine of theta coming out from the top for the x coordinate. And I do the same thing for the y. So sine of theta, cosine of 3 pi over 2 would drop out. We'd have cosine of theta, sine of 3 pi over 2. Which would be negative 1, but we have a negative from the subtraction and another negative from the negative r. So this would be negative r cosine theta. And once again, we're going to be going theta between 0 and 2 pi. Okay. So if I just want to do a quick check to make sure this is doing what I want it to do, I can just plug in, for example, the quadrantal angles. If I plug in 0, I get x is 0, y is negative r. So sure enough, I'm down here at the point 0, negative r. At pi over 2, I would be at negative r, comma 0. So sure enough, I'm over here. At pi, I'd be at x is 0, y is positive r. And at 2 pi, I'm back over to here. So wait a minute, it was 0. Yeah, pi over 2, pi, at 3 pi over 2 rather. At 3 pi over 2, the sine of 3 pi over 2 is negative 1 times negative r, so I'd be at x equals r, and then the cosine there is 0. And then finally at 2 pi, I'm back to where I start. X is 0, y is negative r. So this is in fact doing exactly what I want it to do. Okay. So it's the same kind of orientation reverse and shift that we did in the previous example. So this takes care of the circular motion part. This would be if I were just standing still here and spinning around this way. All right, so now I got that. So how do we incorporate here the horizontal motion? Okay, so as this is rolling down the line here, the x-coordinate is going to be, well, whatever the speed is, velocity rather, times the time. Okay, so the x is going to be velocity times time. That'll tell me the x-coordinate of the center. The y-coordinate of the center is going to be r all the time. Right? So as this ball is rolling, the y-coordinate stays still. Right. So what I need to do is figure out what would this be in terms of theta. Okay, so what would be this? What would this be in terms of theta? So remember, our velocity or our speed here, that's our distance over the time. And if I'm measuring theta in radians, I can get my distance as the radius times the angle theta. So if I take v times t, that's going to be r theta over t times t. That's just going to be r times theta. Okay. So once again, another good advertisement here for radian measure. So what I need to do is I need to take my x and the y, negative r sine theta. That accounts for the rotation. R theta is for the translation. So I'm going to add those two things together. The y was negative r cosine theta. I need to adjust for us always being r units above, so that's going to be r. And then I can factor the r out. We'll put the theta first, minus sine of theta. And we'll take the r out, 1 minus cosine theta. And this is for theta, actually bigger than or equal to 0. Okay, because we can go from 0 to 2 pi, but actually theta is just going to just start at 0. And so these are the classical equations for the cycloid, which we get down to here. Okay. So if we're got a circle of radius 3 that's rolling along, r equals 3. Then I would just substitute in 3 for r. So I got 3 times theta minus sine of theta. Y would be 3 times 1 minus cosine theta. And this would be for theta bigger than or equal to 0. And this should give me the motion here. Now, if you look at the diagram here, it kind of suggests what curve I should get. I should start here, and then as I'm rolling, I should get this arch, right? So as I'm rolling around, let's see if we can get that to match here. We're using t's instead of thetas. That's fine. We got 3 times t minus sine of t, and then we got 3 times 1, was it 1 minus sine of t? Is that right? 1 minus cosine t. And we'll just go from 0 to a. We'll add a slider that starts at 0 and goes to, I don't know, 10 or something. So we can try to imagine this this thing rolling here. So we start off at the bottom, and then as we're rolling around, moving to the right, we create that first arch here. Hits the ground. We're back at the ground, and then we start back up again. And so this is what would happen as we go through, as we're rolling along with that circle. Okay, so we would start here, circle a radius 3. At the bottom, and then as we moved across, we'd be tracing out these arcs. Okay. So that'll do it for the cycloid, and that'll do it for the course.